We now close out the section on real valued functions by looking at some concepts related to maximum and minimum values of functions. We'll first define the terms bounded above and bounded below for functions and maximum and minimum values. We'll provide some graphical examples to give you some visual understanding about what these concepts mean. And then we'll do some proofs related to these concepts. So if you have a function from an interval I to the real numbers and let j, a subset of I, be an interval, we say that f is bounded above on j if there exists some number that is bigger than all the outputs for f. In other words, f of x is less than or equal to m for all x in j. And another way of saying that is if you look at the image of j, that is a bounded above set. And similarly, we say f is bounded below on j if there exists some number m in the real numbers such that f of x is greater than or equal to m for all x in j. And again, that means the image of j is a bounded below set. So to give you a visual understanding of this, here's a bounded above function. All we need is a number big M that is above all the y values in that function. The y values are the outputs. And we can put that m right up there. Similarly, here's bounded below functions. We put the little m below all the points, and we can see that all the points are at least as big as little m. For a more algebraic example, here we have a function from the real numbers to the real numbers, f of x equals x over x squared plus 1. And we want to show that this function is bounded above. So we've got to actually find a bound. Easiest way to find the bound is probably to look at a graph, make a guess. It's pretty clear that f is bounded above by 1 if you look at the graph. But we should prove it by contradiction. So if it is not bounded above by 1, that means there's some x where f of x is bigger than 1. So we'll assume that and we'll prove a contradiction. Well, we know f of x is equal to x over x squared plus 1, so we're going to assume that is greater than 1. And then we're going to do a little bit of algebra. X squared plus 1 is always a positive number, so we can use scaling to multiply both sides by x squared plus 1. And that gives us x is greater than x squared plus 1. If we move that x to the other side of the inequality and flip it around, we get x squared minus x plus 1 is less than 0. This is a perfect opportunity to use some of our inequality techniques. Completing the square is the one I'm going to do this time. If you complete the square, you get x minus 1/2 squared, which is a non-negative number, plus 3/4, which is a positive number. Adding those together, you get a positive number, which is not a negative number, and that's our contradiction. That means that f of x is less than or equal to 1, and so f is bounded above. Now, if you want, you can use a similar argument to show that f of x is greater than or equal to negative 1. So it's actually bounded below as well. But I'm going to let you try that one if you want to. I've done enough work. All right. So now another definition. If we have f, a function from an interval I to the real numbers, we say that f has a maximum value at c if f of x is less than or equal to f of c for all x in I. And we say that f has a minimum at c if f of x is greater than or equal to f of c for all x in I. And for both of those, the value f of c is, in the first case, the maximum value of f, and f of c is the minimum value of f when it's a minimum. So let's see if we can find the maximum and minimum values, or at least one of those. We're going to go for minimum values on this one for the same function that we were looking at before. What is the minimum value? Again, looking at the graph, you might guess that it was negative 1/2. We were being a little bit conservative last time, treating negative 1 as a lower bound, but now we need to be a little bit more precise if we want to find the actual minimum value. So we need two steps. One step is we need to show that it is a lower bound for all the outputs, and then the second one is we need to show that it actually the function actually achieves the value negative 1/2 for one of the outputs. So for the first step, we got to show that f of x is greater than or equal to negative 1/2. And we're going to use the same techniques we did before. We're going to do a proof by contradiction. we're going to assume that f of x is less than negative 1/2. If we plug in the formula for f of x, multiply both sides by x squared plus 1 and by 2, right? Do a little bit of, then we get 2x is less than negative x squared minus 1. Now we're going to move the negative x squared and the minus 1 over to the left-hand side of the inequality because I don't like those negative signs. And we get x squared plus 2x plus 1 is less than 0. That polynomial expression should look familiar. That's a perfect square. And that implies that x plus 1 quantity squared is less than 0. But that is ridiculous because when you square a number, you get a non-negative number. So that's a contradiction. Now step 2, we got to find an x that actually gives us negative 1/2 as a value. That's not too hard. Plug in negative 1, that gives you negative 1/2. And then we're done. That proves that negative 1/2 is the minimum value of x, and we have a minimum at x equals negative 1. So now that you've seen these proofs, I think you're ready to work on the activities for maximum and minimum values. Just go ahead and click on the link below this video.